Welcome back to Discrete Math. I'm Dr. Jeff Groh. Today we're going to talk about the cardinality of sets. We've already talked a little bit about cardinality. If the set S is finite, then the cardinality of the set is the number of elements. Questions we're going to address today are, what's the cardinality of the set of natural numbers? The set is not finite. And does the cardinality of this set match the cardinality of the set of real numbers? We will conclusively show that these are not the same. This set is infinite. This set is also infinite, but we will show that there are different sizes of infinity. So let's go back and look at how it is that we know that two sets have the same size. This set, ABC, has the same number of elements as the set 1, 2, 3. And we know this because we can construct a bijection. The critical element is the existence of this bijection. If, on the other hand, I had ABC 1, 2, only a surjection, if this is my set A and this is my set B, if I had only a surjection, then I would know that the cardinality of B, I guess, is going to be the set containing 1 and 2 in this example, is greater than or equal to the cardinality of B. On the other hand, this is not onto, it's not a surjection, but it is an injection. So in this set, this case, my A is going to be like this. So the cardinality of A is less than or equal to the cardinality of B. So if we have a bijection, 1 to 1 and onto, the cardinalities are the same. If you only have a surjection, then the cardinality of the domain space will be bigger than or equal to the cardinality of the range space. And over here, if you have an injection, then the cardinality of the domain space will be less than or equal to the cardinality of the codomain. So let's formalize these concepts. Sets A and B are called equinumerous. Do you like that word? Or have the same cardinality. If there exists a bijection between them. We can add to that by saying if there is a surjection from A onto B, then the cardinality of A is bigger than or equal to the cardinality of B. If there is an injection from A into B, then the cardinality of A is less than or equal to the cardinality of B. So you can see, if you have a bijection, it's both a surjection and an injection, you must have equality. What does it mean for a set to be finite? a set is finite and has finite cardinality if there is a bijection between it and an initial segment of the natural numbers. We'll define the cardinality of the empty set to be 0. And also, if a set is not finite, then it is infinite. But there's a new notion we need to introduce here. A set is called countably infinite if there exists a bijective correspondence with the set and the natural numbers. We say that this is countably infinite. So for example, suppose my set is 1, 1/2, 1/3, 1/4, and so on. I can make a one-to-one mapping between the natural numbers and this set. I'll say this is the first element, this is the second element, this is the third element, and so on. This will be 1-to-1. It won't be 2-to-1 or 1-to-2, which would be not a function at all. But it'll be 1-to-1, and it will cover the entire set, so it's a 1-to-1 and onto correspondence. So this set is countably infinite. In this case, we say that the cardinality of the set is aleph naught. Here we have the Hebrew letter aleph with a subscript of 0, which we say all for naught. It's all for nothing. Aleph naught. So aleph naught is the cardinality of the set of natural numbers, because the natural numbers are countably infinite. You can make a one-to-one correspondence between the natural numbers and the natural numbers using the identity function. So the natural numbers have cardinality equal to aleph naught. More generally, a set is countable if it is either finite or countably infinite. In either case, you can line them up and count them off, first, second, third, fourth. If it's finite, that comes to a conclusion. If it's countably infinite, it doesn't come to a conclusion but goes on forever. It's pretty easy to see that the whole numbers have the same cardinality as the set of natural numbers. The one-to-one correspondence being shown here. What's even more interesting is that the set of integers also has a one-to-one correspondence with the set of natural numbers. Notice over here we just expanded the set by throwing in one thing, and we don't get anything different in terms of the size. So they're both of cardinality aleph naught. So is the set of integers. I just need to show you how to make that one-to-one correspondence between the integers and the natural numbers. And here's what we'll do. We'll count them off. 1, 2, 3, 4, 5, 6, 7, and so on. We'll just keep oscillating back and forth, and we'll have a one-to-one and onto correspondence between the natural numbers and the set of integers. So we deduce then that the cardinality of the set of integers is the same as the cardinality of the set of natural numbers, which is aleph naught. What about the set of even numbers? Well, we can count these off again, first, second, third, fourth, and so on. So we have our one-to-one correspondence between the even natural numbers and the natural numbers. So the cardinality of the evens will also be equal to the cardinality of the natural numbers, or aleph naught. You may or may not have heard of Hilbert's Hotel, named after one of the most famous mathematicians of all time, David Hilbert. Now, Hilbert's Hotel is interesting because it has a lot of rooms. In fact, this goes on forever. It has a countable infinity of rooms. Now, Hilbert must be fantastic at managing this hotel because currently every single room is occupied. But then one new customer shows up. Can we fit this one new customer in to Hilbert's Hotel? And the answer is yes. We'll just ask everyone to shift down one room, and then this person can go into the newly unoccupied first room in the hotel. Alternatively, let's suppose we have a countable infinity of people show up. How can we fit a countably infinite number of people into Hilbert's Hotel if it is already completely occupied? And the answer is, we'll just ask the person in room 1 to move to room 2, the person in room 2 to move to room 4, the person in room 4 to move to room 6, and so on. They'll go to every other room and occupy those, and then all of these people can fill in the odd room numbers. This might suggest something odd about the arithmetic of these infinite cardinal numbers. In particular, aleph naught plus aleph naught seems to be aleph naught. What about the set of rational numbers? Remember, those are ratios of integers. You'll recall that the set of rational numbers is the set of all p over q, such that p and q are integers and q is not 0. These exactly correspond to the set of points p comma q, such that p and q are integers and q is not 0. Those can be plotted as points on the plane where we're assuming that the y-coordinates can't be 0. So y-coordinate can't be 0. You have to stay off of the x-axis. So 1, 1, 0, 1, negative 1, 1. Oop, have to stay off the x-axis. Do, do, do. Stay off. Do, 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 do. Do, 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 do. Oop. Do, do. And these points, then, we can demonstrate pretty easily, have a one-to-one and onto a bijective correspondence with the set of natural numbers. And we can do that by counting them off. 1, 2, 3, 4, 5, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, and we can keep on going around, spiraling and covering every single point of this form, which will correspond to every single fraction. We deduce then that the cardinality of the set of rational numbers is the same as the cardinality of the set of natural numbers, or aleph naught. We now come to an important theorem. Suppose that A and B are countable. Then the union is countable. The union of countable sets ends up being a countable set. This theorem can even be generalized to say that a countable union of countable sets is also countable. But we're just going to prove this version. And the proof is going to go, we're going to assume first that A intersect B is empty, that these are disjoint sets. And we can do that because, after all, we could take B minus A union A. That gives us the same thing as A union B. And so we may as well assume that we've taken out any common elements, and they are in fact disjoint. From here, we proceed with three cases. In case one, we'll let A and B be finite. In this case, A can be thought of as A1, A2 through AN, and B as B1, B2 through Bn. So what about A union B? A union B is A1, A2 through AN, followed by B1, B2 through Bm. We don't have to have the same number of elements in each of these. And so here's how we'll make our correspondence. We'll say this one corresponds to 1, 2, all the way down to n. This will be n plus 1, n plus 2, all the way down to n plus m. And this will be our one-to-one and onto correspondence with an initial segment of the natural numbers from 1 to n plus m. Therefore, A union B is finite. Its cardinality will in fact be n plus m. And hence, A union B is countable. Because a set is countable if and only if it is either finite or countably infinite. In case 2, we'll assume that A is finite and B is countably infinite. Then how can we take the union of these and make a correspondence with the natural numbers to show that it's countably infinite? And the answer is, we'll just list the elements of A first, and then the elements of B. So 1 goes here, 2, this will correspond to n, this will be n plus 1, n plus 2, and then so on. So the cardinality of A union B will be the same as the cardinality of the natural numbers, or aleph naught. So A union B is countable. And that leaves us case 3. What happens if A and B are both countably infinite? In this case, the correspondence we'll make will be kind of what you would do with Hilbert's Hotel. Let's suppose the rooms are all occupied by members of the set A, and then the members of set B show up. Well, we'll just have the members of set A occupy the odd rooms, and the members of set B occupy the even rooms. Like this. So this will be the first, second, third, fourth, and so on. So the cardinality of A union B will be equal to the cardinality of the natural numbers, or aleph naught. This brings us to the famous Schroeder-Bernstein theorem, which goes like this. If the cardinality of A is less than or equal to B, B's cardinality, and the cardinality of B is less than or equal to the cardinality of A, then the cardinality of A will equal the cardinality of B. What this comes down to is that the cardinality of A being less than or equal to the cardinality of B means that there's an injection from A into B. And the cardinality of B being less than or equal to the cardinality of A means that there's an injection from B into A. From this, it will follow that there is a bijection between A and B, so they have the same cardinality. As an example of an application of the Schroeder-Bernstein theorem, I want to show that the cardinality of the open interval from 0, 1 is the same as the cardinality of the half-open, half-closed interval from 0 to 1. So first, consider f of x equals x. This maps 0, 1 into the other set, and it does so in a one-to-one way. If x1 does not equal x2, then f of x1 will not equal f of x2. And so this is an injection, but it's not onto because it doesn't cover the number 1 over here. But that doesn't matter. It's still an injection, and so we get the cardinality of 0, 1 is less than or equal to the cardinality of 0, 1 with the closed interval on the right. Now, all that's required is to get an injection from this set into this set. So let f of x be x divided by 2. Then this maps 0, 1 into, well, it maps it onto 0, 1 half, which is a subset of 0, 1. And this is an injection. It's easy to see that this line is 1-to-1, satisfies the horizontal line test. So it's an injection, it's 1-to-1, and that means the cardinality of the set 0, 1 is less than or equal to the cardinality of the open interval 0 to 1. Now, by the Schroeder-Bernstein theorem, the cardinalities are the same. Let me give you a maybe not so good definition. A function is called computable if there exists a program in some language that produces the values of the function. Otherwise, it is uncomputable. We're going to prove that there do exist functions that are uncomputable. We're going to argue this first by noting that there are only countably many computer programs. These programs are finite strings of a finite set of symbols. And there can clearly be only a countable number of such things. Second, the number of functions from the set of natural numbers into the set of natural numbers is uncountable. This follows from something called Cantor's theorem. Cantor's theorem says that the cardinality of a set is always strictly less than the cardinality of its power set. Well, if our set is the set of natural numbers, the set of functions from the natural numbers into the natural numbers is the same as the power set of S. Just take a subset of n, let that be the range of a particular function, arranged however you wish. And so the cardinality of the power set of S will be equivalent to the number of functions from n into n. But Cantor's theorem says that there's a strict inequality between them. Now that means if S is equal to n, then over here we have aleph naught. This must be something bigger. This must be something bigger than aleph naught, strictly bigger. If there are only a countable number of programs, but a strictly larger number of functions, then there must be a function that is not computable. We're going to set the cardinality of the real numbers to be C, and we're going to show that C is not aleph naught, that the real numbers do not have the same cardinality as the set of natural numbers. The proof is a proof by contradiction. Suppose the cardinality of the natural numbers is the same as the cardinality of the real numbers. Then there exists a bijection. Between n and r. What does that mean? It means you can count the number of elements in the set of real numbers, or you can list them, first, second, third, and so on. We'll construct our bijection by making the list. We'll start by constructing an injection. We can extend that injection to a bijection, but here's how it goes. We're going to take our function f, and we're not going to cover all of r. We're only going to cover things between 0 and 1. So we're only going to output numbers between 0 and 1. And those numbers always have a decimal representation. This is my first number and its first digit, my first number and its second digit, first number and third digit, and so on. It has a decimal representation like this. This is my second number with first digit, second number, second digit, second number, third digit, and so on. And we keep going on in both directions. So we're going to construct another number, still between 0 and 1, using these numbers here. It's going to be different from the first number in the first digit. Set B1 to be 7 if A11 is less than or equal to 5, and 2 if A11 is greater than 5. And do the same thing for all the others. BK will be 7 if KK is less than or equal to 5, and 2 if AKK is greater than 5. We're only looking at those on the diagonals, which means we can construct this number 0, B1, B2, and so on. And this number, we'll call it R, this number R is not equal to the first number in our list because it differs in this digit. It's not equal to the second number in our list because it's different in the second digit, and so on and so forth. It doesn't equal any of these numbers So because we have this representation, r has to be a number between 0 and 1. But r is not in the list. Now this is a complete list of numbers between 0 and 1 because we said we had a bijection from the natural numbers into that set. So this is a contradiction. We must have made an error, a false assumption along the way. But the only assumption that we've made that could be false is that the cardinality of the set of natural numbers is equal to the cardinality of the set of numbers between 0 and 1. And so we deduce then that the cardinality of the natural numbers is not equal to the cardinality of the numbers between 0 and 1. Now keep in mind, the real line is a union of a countable number of intervals from k to k plus 1. Intervals of the form, closed interval from 0 to 1, that would be in here when k is equal to 0. And so the real line would be a countable union of, if this were countable, it would have to be countably infinite. But we've shown then that this set, each of these sets, which will have to be equinumerous because we can easily make bijections between them, these sets are not countably infinite. They must in fact have some other kind of cardinality. And that's where we'll define the cardinality of the real numbers to be some number c, where c is the cardinality of the continuum, r being the continuum. One of the basic theorems from set theory is that the cardinality of the power set of a set is 2 to the power of the cardinality of the original set. So we see then the cardinality of the power set of the natural numbers will be equal to 2 to the cardinality of the natural numbers, or 2 to the power of aleph naught. We'll define this to be aleph 1. It has to be strictly larger by Cantor's theorem. So aleph naught will be strictly less than aleph 1. Similarly, we can do the power set of the natural numbers and get something strictly larger, aleph 2, and so on and so forth, allowing us to have an infinite number of different infinite cardinalities. You might think there's something suspicious about a theory that splits infinities, which we have done here. We're making many different sizes of infinity. In fact, it was Cantor who came up with this idea of these different sizes of infinities, and his colleague, Kronecker, refused to permit him a position as a professor at the University of Berlin because he so detested this idea of these different sizes of infinity. Kronecker said, God invented the integers, man invented everything else. So he doesn't like this idea of these different infinities, but Cantor provided proofs. This leaves open one additional question. We had the cardinality of the natural numbers and the cardinality of the continuum. The question might be, how big is the cardinality of the continuum? Does it equal aleph 1? Does it equal aleph 2? Is it any of the alephs? Are there other infinities in between the two? There's a famous axiom in set theory called the continuum hypothesis. It says that there are no cardinalities between aleph naught and the cardinality of the continuum. So there's nothing in between. It's been shown that you cannot prove the continuum hypothesis is true. It's also been shown that you cannot disprove the continuum hypothesis. You can't show it's true, you can't show it's false. In other words, it's kind of outside of logic in some very strange way. Logic is insufficient for deciding the truth of this particular proposition. So this has to be taken as an axiom. A lot of mathematicians don't like the continuum hypothesis. They like to assume that there are a large number of infinities between Aleph naught and the cardinality of the continuum. However, if you accept the continuum hypothesis, it's possible to show that the cardinality of the continuum is in fact Aleph 1, which is the that is then the cardinality of the set of real numbers.